we had finished with, we didn't start anything new last time, right? So up until this point, we've assigned the homework 1 through 18. That was the problem set that was due on Sunday. Does anybody have any new questions from that stuff now that you had forced to have completed the homework? Does anything else come up that you were unsure about that you wanted to talk about? Okay, fair enough. Then we will continue on with where we left off in chapter 1. So today we're going to be looking at sections 5 and 6. In section 5, we're going to be talking about symmetry. So if you remember, this whole chapter 1, we started with talking about functions, like what a function is and how to tell if something's a function or not. And then from there, we've talked about like attributes of functions. So we did like, domain and range, and like increasing, decreasing constant, and extrema. And we've just kind of been talking about, like continuity, all these things that are just like properties or descriptions or attributes that a function can have. We're going to continue that discussion today, this time talking about symmetry. So again, this is an attribute that a function can have. So there's 3 types of symmetry that we're going to talk about. The first is symmetry with respect to the x-axis. And I use the abbreviation WRT for with respect to. So WRT just stands for with respect to. That's just an abbreviation I use because, well, in mathematics that phrase comes up quite a bit, and it allows me to get something like this onto one line instead of 2. So let's take a look at something that is symmetric with the x-axis. So we'll start with looking at the equation version of it. So something like x squared is equal to y is an example of something that's symmetric about the y or about the x-axis. However, when I look at this, I don't know, if you say so, Mr. Kulik, that's symmetric about the x-axis, I don't even know what I'd be looking for in an equation. And it's usually not particularly clear, the symmetry, just by looking at the equation. So maybe let's look at a graphical representation of this, right? That might be more informative for us. As this is currently written, is this going to be easy for me to graph? No, right? Why not? What's going to make this hard to graph? I mean, it's not. Oh, I wrote the wrong thing here. My apologies, everyone. It should be written like this. That makes a big difference because you're like, there's no problem with graphing this. That's why you're all silent. That makes a lot more sense if I know one was answering. What's the problem with trying to graph this now? The y isn't by itself, right? So if you try to type this into your calculator, it's not going to work, right? Because we need the y by itself for us to be able to type this into our graphing calculator. So what do we want to do? Go ahead, Jake. Yeah, square root both sides. So we say y is equal to x squared. Does that look good? Oh, too many head shakes. There's something wrong with this. Who sees it? Grace. Yes! A plus or minus. Whenever we square root both sides of an equation, it generates a plus or minus. Don't forget that. Right? You will. It's okay. But I'm going to keep reminding you like every time it happens. And eventually, you should stop forgetting. But, all right. I'm going to sketch a quick graph of this. I'm not going to bother typing this into our calculator. Frankly, because I think we already did this one, or typed this in like a chapter or a section or two ago. So the graph of this is going to look something like this. So what do we mean by symmetric with respect to the x-axis? It means if we think about the x-axis as a mirror, and I take some point on this side of the x-axis, maybe I'll call that point x comma f of x. If I flip that point over the x-axis, I should have the point f or x comma negative f of x. Right? Should have the same x coordinate, but the y coordinate should be its opposite. Kind of visualize that. Okay. What if I represent this as a table instead? So maybe we pick the x's 0, 1, 4, 9. So when I plug those x's in, well, when I plug 0 in, I get plus or minus 0, but 0 is neither positive nor negative, so the plus or minus really does nothing there. And then if I plug 1 in, the square root of plus or minus the square root of 1 is plus or minus 1. So I'm getting like 2 y values there. Similarly, when I plug 4 in, plus or minus the square root of 4 is negative 2 and positive 2. The plus or minus square root of 9 is negative 3 and positive 3. So I'm getting like multiple y's for almost all the x's, right? What do you notice about the graph of this function up here? Or the graph of this? Okay, it is symmetrical. Think back, what? Yeah, this doesn't represent a function, right? Why not? Yeah, it fails the vertical line test. Very good.
This is a little longer. I can pick up the tablet.
Sure. Okay. So, great. So, because inherently anything that's symmetric about the x-axis is kind of, almost always not a function. This is the least interesting of these symmetries to us. But we should make the observation of what are we seeing with respect to the coordinates? So what we're seeing here is that if I take some value of f of x and I negate it, I should get another value of f of x, right? Like if I have negative 1 and I negate that, I get positive 1. That's a point. That's also a y coordinate in our graph. Everybody agree with that? Or if I take positive 3 and I negate it, I get negative 3, which is also a y coordinate in our graph. Everybody kind of seeing that? The next type of symmetry we're going to talk about is symmetry with respect to, anybody with a guess? No guesses? We just talked about with respect to the x-axis. Y-axis is next. Yes, sir. Yeah, if you got it, just shout it out. That's okay. Now, this particular type of symmetry has a special nickname. We say that functions with this type of symmetry are even functions. In mathematics, we love to have lots of different names for things because, well, even is a whole lot shorter than another thing. Now, why not just start with even? Well, it's because we started with the more descriptive term, and then once we're clear as to like how this would work in context, we come up with the shortcut, the nickname, right? All right, we'll do the same thing. Let's look at some examples. So an example of a function with symmetry with respect to the y-axis might be, let's use f of x's here. F of x equals x squared. That, remember, is fine to type in our calculator. Remember, f of x and y kind of can be used interchangeably. There's not really much difference. The f of x tells us a little bit more like implied stuff where it's explicit about what's the independent, dependent variable, but ostensibly they're mean the same thing, y and f of x. And so let's take a look at the graph. So the graph of y equals x squared should look like this. So this time, if I imagine the y-axis is a mirror, if I pick some point here, say x comma f of x, on one side of the x-axis, and I reflect it across the x-axis, well, I'm in the second quadrant, so my x-coordinate should now be negative, but the y-coordinate should have remained the same. Everybody kind of see that if we're just flipping it across? So just like before, let's write maybe an XY table to kind of look at what's going on with these coordinates. So just pick some x's. When I plug those in, -3 squared is 9, -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. And if I look, I notice that, hey, when I do -3 and +3, when I plug those in, I'm getting the same y-coordinate each time, right? When I plug in -2 and +2, I get the same y-coordinate each time. And when I plug in -1 and +1, again, I'm getting that same y-coordinate. So what is this really telling me? Well, it's saying that f of -x should just give me f of x, right? When I plug -3 in, I get the same y-coordinate as if I plugged +3 in. Is everybody okay with that? So far, so good. Okay. The third type of symmetry that we're going to look at is 180-degree point symmetry. With respect to the origin. Yikes, that's a mouthful, Mr. Kulik. Sure is, guys. So we're just going to call those guys odd. So if a function has this type of symmetry, we'll just refer to it as an odd function. And you're like, now I see why we're coming up with different names for these, because woof, that is a mouthful. We'll do the same thing we did before. We'll look at a couple of different ways of representing this function to kind of get a feel for what it is that we should be noticing. So an example of an equation that represents an odd function would be y equals x cubed, or f of x equals x cubed. Again, y and f of x kind of can be used interchangeably because they basically mean the same thing. And if I look at the graph of this then, it would look kind of like this. So what does this 180-degree point symmetry with respect to 0, 0 mean? Well, let's say I pick some point on the graph that's not the origin. And then let's say I create an anchor at the origin and tie a rope to that other point. And then I rotate that like 180 degrees. Remember, 180 degrees is like half a circle or a straight line from geometry. You guys remember that? That means that I should be landing on the graph again. Because we're in the third quadrant now, that point should be at negative x and negative f of x, right? The x should be negative and the y should be negative because we're in the third quadrant. You guys kind of see that? Now, equivalently to this is if I imagine a reflection across the x, and then a reflection across the y, I'd be able to get to the same thing, right? So that's the same thing as a 180-degree rotation. It's just a reflection from the x and then a reflection across the y. Or you could go reflect across the y first and then or reflect across the x first and then the y, or the y and then the x. You'll get to the same spot. You might remember that from geometry. I think you do a section in there where you talk about transformations, and you talk about rotational transformation being the same as one of these like composite of two reflections. If you don't remember that, don't worry about it. It's like one section from a class 2 years ago. So like if you like, Mr. Kulik, if you say so, we did it, that's okay. Like it's immaterial. I'm just trying to connect ideas to things you may have remembered from before. But if you don't remember it, don't worry about it because it doesn't really add anything, right? Ideally, we want to connect all this stuff to things we've seen before. And I try very hard to like back the truck up to something that's familiar, try to connect it to, because, well, that's how I like to learn, is everything is connected. So instead of having like a pile of papers in my brain, I have like a nice file cabinet where everything is like organized together. Some of us are just like a pile of papers. I'm not that person. That never worked for me. Anyways, let's go ahead and make a table here of values so we can kind of see what's happening. Let's say we use the x's -3, -2, -1, 0, +1, +2, +3. If I plug these in for x, I'd have -3 cubed, which is -27, -2 cubed, which is -8, -1 cubed, which is -1, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, and 3 cubed is 27. So just like we should notice is if I take -3 for x, I'm getting the same y coordinate as I did for +3, but they're the opposite, right? So what I'm saying here, the observation is that f of -x should be negative f of x. If I plug -3 in for x, I should get just the negative of what I got when I plugged +3 in, right? Does everybody feel okay about the names and like the shape of what you're looking for? It's usually not too hard. Most of us are pretty good visually. That tends to be pretty comfortable. Let's do some examples now. And I'm going to add a little bit to this problem. So we're going to determine whether the following functions are odd, even, or neither, and then prove that. So I'm adding an extra step there to the end. So we have 3 examples that we're going to work on, A, B, and C. So the first thing I would want to do is I want to determine, well, what should I be trying to prove? Do I think this thing is odd or even or neither? And then how am I going to figure out which one of those 3 it would be? So that's what I want to start, is trying to figure out which one it is. Which one of the 3 representations that I show you is the easiest to kind of see what it was? I mean, the graph, right? So guess what my first step's going to be? Graph it and look at the picture. You got it. At this point, we've done a lot of graphing on our calculator, right? Hopefully we feel pretty good about doing this. I'm going to start by pressing the y equals button. I'm going to clear out anything I might have had in there. And I'm just going to type in my equation exactly as it looks on my sheet of paper. And then, I don't know, I use my graphing calculator like all day for every class, so I don't know what my window looks like because I can't remember what the last thing I was doing with it was. So I'm just going to do zoom standard instead of graph because I don't remember if I changed the window recently or not. You guys will probably be safe to just hit zoom or to hit graph and not worry about it, but if you're ever in doubt, just a zoom standard usually gets you back to a decent window. So if I take a look at this, what do we see here? Do we see any kind of symmetry? Yeah, this looks like even symmetry to me, right? Looks like an even function because we're symmetric about the y-axis. The y-axis looks like it's dividing this function into 2 identical halves. You guys all buy that? And that should be easy to see with our eyeballs. Not much to do there. So now let's do the proof part. So we need to remind ourselves, what is it that I would need to do to show that this thing is even, to prove it? Well, to me, the piece that seems the easiest to use to do this is my observation. Because I'm given an f of x, right? I know what f of x is. So if I can show this, I'm good. So the first thing I'd want to do is I'm going to state down what I want to show. So WTS, oh boy, WTS is just short for want to show. So I'm just going to remind myself what it is I'm trying to do here. So I want to show that f of negative x is equal to f of x. So when I want to show an equation is true, typically what we want to do is we want to start by writing down what the left-hand side is, and then we'll do some algebra, some simplification, and try to end up at the right-hand side. And we're just going to string it together with a bunch of equalities. Everybody's okay with that? All right. So we'll start with f of negative x. What should I do if I write down f of negative x? What is that telling us to do? It doesn't mean the inverse. Let's do this as an aside. Let me ask you a different question that'll kind of get us moving in the right direction. What if I just had you do f of negative 2? What does that tell us to do? Exactly, yeah, we're going to plug negative 2 in for the x value. So our function was x to the 4th plus 1. So we'd replace the x's with negative 2's, right? So what am I going to do if I have f of x, or f of negative x? I'm sorry. If I have f of negative x, what should I do? Sarah? Replace all the x's with negative x. Exactly right. So in place of the x, I'm going to write a negative x. I still have to the 4th, and I still get the plus 1. Everybody feel okay there? Okay. Now I'm going to work on simplifying this. How do I simplify negative x to the 4th? Well, what does it mean to be to the 4th power when I write negative x to the 4th like that? What does that really mean?
Negative x 4 times.
Good. Negative x times negative x times negative x times negative x, right? Excellent. Now, I have 4 things that are negative, right? If I multiply 4 negatives together, what do I get? A positive, right? If I multiply 4 negatives together, I get a positive. Everybody agree? Okay. And if I multiply 4 x's together, then what do I get?
4x.
Not 4x, x to the 4th. You're right. If I added 4 x's, I'd get or 4x. If I multiply 4 x's, I get x to the 4th. Everybody okay so far? And hey, hold on. Wait a minute. Wait a minute here. I just got x to the 4th, right? What is x to the 4th plus 1? Isn't that just f of x? Actually, let me change my color coding. That should be green. Would make more sense. So what do I have here? We started with f of negative x, and we've shown that that's equal to f of x. That's what we wanted. We're done. That's it. We did it. Everybody okay with kind of what we accomplished here? Okay. Again, if you're not quite sure, if you want to ask a question, just interrupt. No big deal. Let's do part B now. So again, we're going to start the same way. We'll start by graphing this on our calculator. So 2x to the 3rd plus 3x. I hit graph. What does this look like here? Odd, even, or neither? This looks like odd to me, right? Where I have something in each like catty corner quadrants, and it looks like kind of the same shape in each quadrant, right? When I say catty corner, I mean like diagonal to each other, right? Do people still say that? Sure. Kitty, catty, you know. Maybe if you don't live in someplace where there's like blocks, we don't say that anymore. I don't know. All right, the point of the matter is we should have noticed that was odd. That looked odd. So we'll start our proof, and we begin by just writing down what we want to show. Okay, so if I go back and I look, this is what I need, right? So just like for even, I'm going to use that observation that we made about odds. And I want to show that f of negative x is equal to negative f of x. Except this time, let's not use f, because what letter did we use in the problem for g or for b? We called that g of x. So I'm going to make those g's, just so it doesn't get confusing, right? The problem was g of x, so I'm going to use g's when I state that. Okay. Everybody still good? All right, here we go. Start with the left-hand side, so I want to do g of negative x. Just like we did before, I'm going to plug negative x in place of all the x's. So I'm going to still have the 2, but in place of x, I'm going to write negative x. I still have the third power, still have the plus, still have the 3, but instead of x, I'm going to write negative x. Right? Because this was what my g of x is. Everybody's good? Okay. All right. So, it's simplifying time. How do I simplify negative x to the third? What does that simplify to? I mean, Mr. Kulik is just negative x to the third, isn't it? 3 negatives make a negative, and x times x times x is x to the third, so I should just have negative x to the third. When I multiply it by the 2 out front, I'd have negative 2x to the third. Everybody's okay there? When I do 3 times negative x, what do I get? Negative 3x. So far, so good. Now, I'm trying to get to negative g of x, right? That's where I want to end up. So what I'm going to do now that I've simplified is I'm going to factor off a negative. So I can make that negative out front. So if I factor off a negative, negative 2x cubed becomes positive 2x cubed. Yep. And negative 3x becomes positive 3x. Everybody feel okay here? And if I look at this, that is exactly g of x. And since I have the negative out front, what I have here is just negative g of x. And I'm done. I want to make that negative sign real fat there so I don't forget to write it down. Right, it's that same negative sign that we just factored out. That wasn't so bad, right? We can do these. Let's look at the last example. If you were to make a bet, what do you think it's going to be? Neither, right? This is like Teacher 101. The question says it could be one of 3 things. There's 3 questions. I bet each one of them is going to be one of those 3 things, right? I'm done, Mr. Kulik. Oh, come on now. Let's do it for real. Pretend that we didn't know that. All right, so I'm going to go ahead and type the equation in. So 4x squared minus 3x plus 9 I'm going to hit graph and take a look. Oh, I just have this little thing up here. That's kind of disappointing. I can't really tell very well what's going on here. Can you? I need to see some more of the stuff that would be off the screen here, right? So I'm going to change my window so that I can see that. To do that, the X's are fine, right? This graph is plenty wide enough. It just, my picture isn't tall enough. You guys agree with that? So up and down is controlled by the Y's, and the up part of the up and down is the Y max. I'm just going to change that Y max to be a bigger number. Let's say 20. And I'll hit graph. There we go. That should be enough to tell what's going on. Odd, even, or neither. What do you guys think? Probably between even and neither, right? Which one is it? Neither is correct. Why isn't it even, though? It kind of looks like the even one we just looked at. Yeah, so the y-axis doesn't split it exactly in half, right? It looks like there's a little bit more graph on the right-hand side than on the left-hand side. You guys see that? Even though the shape of the graph is the same, we care about where the y-axis is splitting it. It can't be even if the y-axis doesn't split it exactly in half. Cool? Okay. So this looks like a neither, we've decided. So to show it's neither, we have to do two things. We have to show it's not even, and we have to show that it's not odd. Is everybody okay with this? That we need to do two things here. All right. So we'll start with just h of negative x. And I'm going to go ahead and do the same thing I've done before. I'm going to replace all the x's in my equation with negative x's. I'm now going to simplify. Negative x squared is negative x times negative x is going to be positive x squared, right? So I'm going to have 4x squared. Negative 3 times negative x is positive 3x. And then the plus 9 just stays where it is. Now, if I look at this, I notice that this is not equal to h of x. Because the signs on the 3x's were different, right? So I conclude right here that we're not even. Okay, I'm going to keep going now. I'm going to factor off a negative sign to check to see if it's odd. So if I factor a negative sign out, the sign on each one of these is going to flip. So positive 4x squared becomes negative 4x squared. Positive 3x becomes negative 3x. And positive 9x becomes negative 9x. Or I'm sorry, positive 9 becomes negative 9. Everybody's okay with that? And this is not equal to negative h of x, because that should be negative 4x squared minus 3x plus 9. What do I notice is different? The sign on the 4x squared and the sign on the 9 are different. Everybody agree? So I conclude that this is not odd. Since h of x is not even and not odd, it is neither. And we're done, right? We feel okay on this? Okay. We're good with that, like what the algebra is showing and kind of what I'm trying to accomplish there. That can be hard for some people, and if it is hard, that's okay. But speak up if you're like mega confused and you don't know, you don't see what it is exactly that we are trying to do here. Yes, of course, yeah. Okay. If you change your mind later after you look at the homework, that's totally fine also. We can certainly talk about it next time. At this point, you guys have done enough that you should be able to do 19 through 22. But we're not done yet for today. We're also going to talk about section 1.6. This section is about asymptotes. Do you guys remember this word asymptote from last year? I ask that because I know that some of us had a variety of a different Algebra 2 experience, right? Some of us had one teacher that was pretty good the whole year. Some of us had 2 or 3 teachers and it was kind of a mess and might not have accomplished as much because of all the transition between peoples, right? So are there some of us that didn't talk about asymptotes last year? You're not sure? Okay. Well, we're going to approach it as if nobody had heard of them before. So when we say an asymptote of a graph is a line that the graph approaches but never touches. These asymptotes are typically horizontal or vertical. In mathematics, the word approaches means the graph gets closer and closer to the given line, but maybe not actually ever gets there. Notice that I have this little asterisk next to the horizontal. I have that there because for the sake of simplicity in this course, we're going to still consider things to be horizontal asymptotes, even if the graph touches that line, as long as at the ends, the graph is doing that approach but not touch. But it might cross in the middle, and that's still okay. We'll still call that a horizontal asymptote as far as this class goes. So far, so good? Okay. Let's look at a picture to kind of visualize what's going on, because again, this is a visual thing. So the example we're going to look at is f of x equals x squared plus 3x minus 3 over x squared plus 2x minus 3. This is an example of a rational function. Maybe you guys remember that term from Algebra 2 last year. Hopefully you remember talking about these a little bit. Would have been right towards the end of the year. I'm going to graph this function, but I'm going to do it using this different piece of software rather than my graphing calculator. The reason I'm doing that is I want to drop an image of this graph into OneNote so I can draw on it. And the quality of image I'm going to get is much better with this program than like screen grabbing it off my calculator. So that's the only reason why I'm doing this. We'll graph it on the calculator too in a minute. This program that I'm using right here is called Graphmatica. It's a free download, but I don't think you guys have download rights to your tablet, so you'd have to get like permission from some IT administrator or something to download it if you wanted to have it on your computer also, but it's pretty neat. It generates nice, a nice picture like this you could drop into OneNote. The other advantage of it also, this is the best part as far as I'm concerned. Remember how we couldn't graph stuff like x equals y squared on our calculator? You can do it on Graphmatica with no adjustment. So that's kind of nice. Anyways, that's beside the point. All right, so I'm looking at this thing. If I look at this, I see I see 3 asymptotes. So I see a vertical asymptote appearing here at x equals 3. This is a vertical one because it's going up and down. Again, notice that like the graph's getting close to that vertical line, but it doesn't ever look like it's going to cross it. Everybody good? Okay. I see another vertical asymptote at what looks like x equals 1. And then I see a horizontal asymptote at what looks like y equals 1. Now I want to point out to you, again, notice that the graph is definitely crossing the line y equals 1 here in the middle. Still refer to these as asymptotes, even if that's happening, because what I care about is that it's having that getting close to but not crossing behavior at the ends. Okay, I don't care what happened in the middle. I only care about what's happening at the ends for a horizontal. Why don't I ever have to worry about this for a vertical? What would happen if the graph crossed in the middle of a vertical asymptote? It couldn't be a function anymore, right? So, not a big deal. All right. So, just as a little reminder from like Algebra 1, we name vertical lines x equals because every point on this vertical line has the same x coordinate, in this case, -3. So we write x equals -3 because every point on that vertical line has the x coordinate -3. Similarly, we name horizontal lines y equals because, again, if I look at any point on this horizontal line, they all have the same y coordinate, that being +1. So we name it y equals +1 because every y is the same. Everybody's okay with that? Great. Yeah, of course. All right. So easy enough to see these visually, right? You guys agree? Pretty straightforward. What we're going to do now is confirm these asymptotes by using a table of values. Okay, so this would be like potentially if Mr. Kulik gave you a problem like this on a test or a quiz or whatever, this would be like how you'd show your work, right? So let's start with the vertical asymptote x equals -3. So I'm going to make like an xy table here. So the x's I want to choose need to be getting closer and closer to -3. Now there's two sides I can approach -3 from. I can approach it from the left with values that are smaller than -3. So maybe I start with -3.1 and then -3.01 and -3.001. You see how I'm getting closer to -3, but never passing -3, right? Now I'm going to I'm going to look at the other side of -3. So I'm going to start with numbers that are bigger than -3 and get closer and closer to -3. So maybe I'll start with -2.9, and then we'll do -2.99 and -2.999. So far, so good? How am I going to find the y coordinates for this? I have to plug those values for x into my function. Does that look like a lot of fun? Right? Wouldn't it be nice if there's a way to tell my calculator just like, hey, just plug -3.1 into this and tell me the answer? Yeah, it would, wouldn't it? Guess what? There is a way to do that. Let's look at how to do that. Because this is a time saver right here, folks. All right, I'm going to start by going to my y equals menu. I'm going to clear out anything that's in there, and I'm going to type in my function exactly like it looks like on my sheet of paper. Notice on this problem, I have this horizontal fraction bar in my problem. To get a horizontal fraction bar into your calculator, the easiest way to do that is to press alpha, and then y equals, and then option 1. And there's the horizontal fraction bar. So now you can just continue typing this exactly like it looks like on your sheet of paper. When you're ready to move down to the lower level, you just use the down arrow. That is a wonderful little tool for you. It makes it much, much easier to type these things in a way that you know what you've got, rather than have to muck around with a bunch of parentheses. If you wanted to type this thing in using a division symbol, you need a parenthesis around the entire numerator, then the division slash, and then a parenthesis around the entire denominator. Easy to mess up those parentheses. I like to just use that horizontal fraction bar so it can just look exactly like my sheet of paper. Okay, before I hit go here, I'm going to take a look at the graph and make sure that I typed this in correctly, because I should see an asymptote at -3, +1, and then a horizontal asymptote at 1. That looks like about what I'm seeing there, so I'm pretty convinced I got this right. All right. So what I've done now is I've typed in my function into the y1 spot. The calculator will treat that y1 as like a function notation. So if I wanted to do like, if I wanted to plug -3.1 in, it would, what I want to do is I want to type this, and it'll do that plugging in for me and just spit out whatever that number is. Okay? So that's the notation that we're going to use. Let's do this. All right, so how do I get that y1 on my calculator? So here's what you need to do. You're going to start by pressing the vars button, which is right under the down arrow. Vars is just short for variables. The variable we're looking for is called y1. That's a y variable, so at the top here where it says y vars, I'm going to move over to that tab that says y vars. And currently our calculator is in function mode, so I'm going to select function. And there's the y1. So I'll press enter to select that. And then I'll say, okay, y1 of negative 3.1, just like I would for a function notation. And there's my number, negative 656. Now, you're probably thinking to yourself, yo, Mr. Kulik, that was a lot of menus to jump through to get that y1. Isn't there a better way of doing it? Well, once you've done it once, since we're going to be doing this a whole bunch of times, I can just press second and the enter button. That'll recall the last thing that I typed. So I can just go and edit that line to just turn it into negative 301 and press enter, and I don't have to jump through any menus. And then I can do the same thing. I can press second and enter again and update that to be 3001 and just press enter again. So if I look at these y values, as we're getting closer and closer to negative 3 on the left side of negative 3, those y values are getting smaller and smaller and smaller, right? And they're getting smaller quite quickly, right? I'm almost changing by a factor of 10 each time. What is that telling me? That the y value is heading kind of towards negative infinity there, right? They're getting bigger and bigger, smaller and smaller and smaller, and appear to be doing so without bound, right? Everybody okay with that? Now I'm going to do the other three. Again, I'm just going to press second and enter, and then move my cursor over and just update what I have here. I'll type all three of them there real quick and type and write that down. So what do we have here? 844, 75, 94, 750, 94. And here I notice kind of the same thing is happening, except here the y's are getting very big. So they're approaching positive infinity this time. When I see this, where both sides are going, or even one side going to an infinity, that tells me I have a vertical asymptote. Okay. I'm now going to check x equals negative 1. So I'm going to do the same thing, kind of set up a table. So I'm going to start with something that's a little less than negative 1. So like negative 1.1. And then get progressively closer to negative 1. Then I'll move and I'll start something. Was that negative 1 or positive 1? It was positive, wasn't it? Oops-a-daisy. Erase those. That was positive 1. So something smaller than it would be like 0.9, and then 0.99, and 0.999. And then bigger than it would be 1.1, 1.01, and 1.001. Oops-a-daisies. Sorry about that. Does it matter if you do left side first, then right side, or right side first, then left side? No, man. I just like to go from small to big because that's what it's, it seems weird to me to not. All right, so same thing, second and enter, and now I'm just going to go and turn that into 0.9. And then 0.99. And then 0.999. So I have negative 1.31, negative 2381, and then negative 248.81. Again, here we see the y's getting very small very quickly. Now let's do the other side. So again, second and enter, and we'll just edit what we had. So 368, 2619, and 251.19. Again, here we have getting big very quickly. Either of those is going to tell you have a vertical asymptote there. So far, so good. Got one more asymptote to confirm. That's y equals 0. This one's going to be a little bit different, though, because I have a horizontal asymptote as opposed to a vertical asymptote. So if we go back and we look at our graph here for a moment, the asymptote here is approaching a y value as opposed to an x, right? What is happening to the x values at that end? The x's are getting really big, right? So that's what I'm going to do, is I'm going to pick progressively larger and larger and larger x's. And to cover this end, I'm going to pick progressively smaller and smaller and smaller x's to find the y's. Okay with that? Instead of getting close to a specific x value, we want to get close to really big or really small x values. So maybe we'll do -10, and then -100, and a -1,000. And we'll do +10, +100, +1,000. Sound okay there? Again, there's nothing magic about these particular numbers you could use. You could have done like -6.2, -248, and then -7,815, right? There's nothing magic about these. It's just like, it looks systematic. It's easy to type them into my calculator with like minimal editing. That's why I choose them this way. Mostly because it's easy to get them into my calculator. But there's nothing magic about these numbers I'm using. Okay, second enter. I'm going to update that, turn it into -10. Press enter. Fiddlesticks. Why did it give me a fraction all of a sudden? What do I really want here? I want a decimal, man. So this is what I'm going to do. Second enter, and I'm going to press the math button. And I'm going to choose that decimal option. That's going to tell the calculator, just give it to me as a decimal, man. There we go. Now here's the catch. If I press second and enter again, if I want to add that 0 in, I want to make sure that I'm inserting a number here instead of just overwriting it, because I don't want to have to go back and put that decimal thing at the end every time. So if I press second and the delete key, above the delete in blue is INS, that's short for insert. When I press that, notice my cursor changes from flashing black to flashing white. What that means is I can now type without having it overwrite. So I've just added an extra 0 in there. And I'm going to do the same thing again. Insert and add another 0 in. So those are those values. So it looks like we're heading towards 1 there. And then we'll do the same thing here. Oh boy. Let's do this one. I'm going to go from the bottom up, I think. Oops. That's not what I wanted it to do. I wanted to delete that. Just so I don't have to do so many inserts. So there's plugging in 1,000. And then if I do it this way, I just have to delete out a 0. And I don't have to muck around with the inserts. It's a little less button pushing. So there we go. So I have 1.085, 1.009, and then I have 1.0009. Again, going to y equals 1, and that's my indication that I have a horizontal asymptote. is that both of these are going to the kind of the same value. What do you guys think? Other than being kind of tedious grinding through the calculator piece, it's not really difficult, though, what I'm asking you to do here, right? That's it for 6-1. So at this point, you guys should be able to do 23 and 24 from 6-1. I also have made you guys have a Delta Math assignment for this chapter that I'm going to announce. Take a deep breath. It'll all be okay. So this Delta Math assignment has like 6 kinds of problems in it. You have to do 4 correct of each type. There's no penalty for wrong responses. It's not graded on the number of tries. You have infinitely many tries. There's no penalty for wrong answers. You don't have to get 4 in a row correct. So at this point, determining if something's a function, you can do that. We've done that already. Writing things in interval notation, you can do that. We've done that already. Appropriate domain for real-world functions, you can do that. We've talked about that already. The last 3 we haven't really gotten to yet, so if you want to pick away at the Delta Math so you're not doing it all at once, great. Those first 3 sets of questions should be fine to do right now. If you get to something like, yo, I don't know what to do with this, just stop and wait, or skip to the next section of questions and try those. If you're like, oh, I don't remember interval notation right now, let me do this other one first, that's fine. But we'll talk about this other stuff is all going to happen in like 1.7, which is what we'll work on for part of next time. That's a big section, so we'll take more than one class to kind of handle that. Everybody cool? Okay. The Delta Math is tentatively scheduled for Sunday as a due date. So again, letting you know early, pick away at it. Don't try to sit down and do it all at once if it's frustrating. Do a little bit and then take a break and come back. It saves your progress. You don't have to finish it all in one setting, right? Everybody's okay? I mean, think about it this way. Right now, what have I assigned? I've assigned 6 homework problems and a Delta Math. That's going to be it for the week, right? That's going to be what's due on Sunday. Because anything we do tomorrow in class wouldn't be due until the next due date. That's not bad, right? We can handle that. 6 problems and a Delta Math. Okay. It's like 30 total problems for a week. Okay. When you put it that way, Mr. Kulik, all right, I don't like the Delta Math part because it's frustrating for me, but it's not so bad. I tried to pick problems where the frustration level should be rather low. Many of them are pretty easy to understand how to answer it correctly. I know sometimes what they want for an answer can be kind of obscure, but these ones aren't too bad. Probably the hardest one is going to be the appropriate domain for real-world functions, but that's a good one. I like those questions. So, all right, I'm done. What do you got? Like